Timer management at transport layer is very difficult. The TCP is very difficult compared to data link layer. In data link layer, it deals with only hop to hop. Hop to hop means there will be one node here and one node, and it is very easy to find out what is propagation delay, and from the propagation delay I can find out round trip time. Round trip time means if I send a packet there and getting back the acknowledgement as just 2 into propagation delay, and then I can find out the timeout as 2 into round trip time, and everything is very straightforward because there is only one link and I know D by B, right? So everything is very straightforward. So when you are sending a packet, you are very sure that the packet will reach the other side in TP time, and you are very sure that acknowledgement will come back to you in round trip time, and you are very sure that if the acknowledgement doesn't come back even in this grace time, which means 2 into round trip time, then the packet is lost. But the problem with transport layer is you cannot have any such derivation procedure. The reason is in transport layer it is end to end. So there can be any number of routers on the way, and there can be any number of hops, and we don't know how many hops are there and what is the total propagation delay on the hops, and how much is the this processing delay, and what is the total round trip time. It is very difficult and messy to find it out, right? And moreover, in one hop, if you find it out one time, then that is enough that you can use it for the entire communication, the same number. But in transport layer, if you find out the timeout or propagation delay once, there is no guarantee that that propagation delay is going to be constant. The reason is you might change the path continuously because IP is a datagram service, which means there is no guarantee that your packet is going to follow the same path all the time. It can take a different path, or the traffic is also going to change, which means as the time gradually increases, the traffic may increase or decrease. Therefore, static timeout timers cannot be used at TCP. So at TCP, timeout timer setting is very important, and if you don't take care while setting the timeout timer, it might lead to congestion. So in 1980s, without this dynamic setting, people have faced lots of problems. Later, Jacobson and other scientists, they worked on this area and they have improved the congestion control a lot. So one way to improve the congestion is, or one way to control the congestion is by using or by setting appropriately the timers. So how this one works is like this. Now let's see what happens if you don't have a dynamic setting here. Assume that early morning 4 o'clock, you started communication with some server, let us say Facebook, early morning 4 o'clock. Then you found out that when you send a packet, the packet is coming back very fast. So depending on that, let us say you have set the timeout as 10 milliseconds. Early morning 10 millisecond timeout is working fine. The packet is coming within time. And later gradually the time is, this is at 4 AM, it is working fine. And gradually at 6 PM, if you again use 10 millisecond as the timeout, the traffic would have increased a lot. Therefore, whenever you send a packet, the packet may not come in time. The acknowledgement might not come in time. The acknowledgement might get delayed because of heavy traffic. Actually, the packet is not lost or acknowledgement is not lost. The acknowledgement is coming, but it is slow because of the heavy traffic. But then if you assume that at this point the packet is lost and you unnecessarily retransmit the same packet, right? See, already data is sent, data let us say D10 is sent, and again you are sending the same data D10, even though the packet is not lost. So you will keep on retrans. Next time what happens is, again you will wait for the 10 milliseconds and this will not come, and you will again send the same packet. The acknowledgement will not come in time, right? So actually here the packet loss has not happened, but you are keep on retransmitting the same packet over and again. So there is no congestion as of now. There is heavy traffic, that's it. But then what you are trying to do is, you are sending one packet many times. Now if everyone tries to do the same thing, one packet, if they are sending it 10 times, then obviously traffic is going to increase 10 times. Already traffic is more. You should have stopped and waited for more time, but patiently, but you are very impatient and you are directly sending the packet many times. So it might lead to congestion. There is no congestion previously, but because of your timeout timer settings, this might lead to a congestion, right? So that is why it is a very big problem. So what you should have done in this case is, instead of retransmitting it, which means whenever you examine that the timeout is happening, then you should have increased your timeout timer and waited for a long time. As the traffic increases, you should gradually increase your timeout timer instead of directly retransmitting the packet. So if I use any such dynamic settings where timeout timer is not static, timeout timer is going to increase or decrease depending on the traffic, then it is going to be better, right? So that is how timeout timer is set at TCP. Let's see, there are various algorithms which are used to set this timeout timer. One algorithm is basic algorithm, and then other algorithm is Jacobson's algorithm. Now we shall examine these two algorithms, and then the third one is cons modification, but let's see these two first, basic, Jacobson's, and then let's go to cons modification of this. Okay.